Welcome everybody. This is the HAccIoT Heterogeneous Hardware Acceleration for the Edge and IoT session. And in this session, we are basically going to present the VEDLIoT project. This is the agenda here, but before we go into that, I would like to welcome not only you, but we are also on Zoom. So our Zoomers that are on the other side and couldn't attend, they are there. And we will be taking also questions from their side via text. Okay, so the agenda for today, we have three presentations coming up in this session. So I'll start with the introduction to the project. Then we will follow with a presentation on the hardware platforms from Kevin. And then at the end, presentation on the performance evaluation and reconfigurability by Mario. So without further ado, let's see. There is something here. Yep.
I'm sorry.
Oh, I think it's the recording.
Yeah, it's a recording.
Okay, good. So now we need to be serious. Okay, so like I said, let's start with the first presentation, which is an introduction to VEDLIoT. So VEDLIoT is the acronym for Very Efficient Deep Learning in IoT. This is a European Union-sponsored project with several partners that you see here, the logos from. So Bielefeld, who is coordinating, and then VEDLiOT is a startup company in Sweden. Chalmers, where I come myself from, so I'm a professor at the Computer Science Engineering Department in Chalmers. Siemens, Christman, University of Neuchâtel, University of Osnabrück, Veoneer, University of Göteborg, Rice from Sweden also, and HAccIoT from Portugal, and Micro. So what is the motivation for VEDLIoT? As you all know, I don't need to motivate you on this, but deep learning is everywhere. So we need to make it faster. That's the punchline. So solve more challenging and more complex problems everywhere. And I'll show you some use cases we are focusing on. And how to achieve this is by providing the whole system to do it. So from top to bottom. And that's our goal. So we are to offer a framework for the next generation internet based on IoT devices, collaboratively solve complex deep learning applications across a distributed system. So that's a mouthful, but I hope you can digest this in the next slides. So again, what we are focusing on here is the platform. So from the bottom hardware, that we will have full systems that we can integrate accelerators in, heterogeneous by choice, so lots of different types of devices, as we will cover in these presentations, accelerators that are specially designed and dedicated for the applications that we are talking about, and the tool chain where we can submit our work, be optimized for this special hardware, and also analyze performance and other interesting things. This is all driven by the use cases, and we have three main use cases. So industrial IoT, automotive, and smart home. And I'll also give some little information about that. And one of the important characteristics of this project, I must mention, is that we are offering an open call for universities or companies to join our efforts and use the technology that we are developing. This is, application time is running out, but if you are interested in this type of collaboration with the project, please contact one of us while we are here or send us an email later on. So in order to get the big picture, this is our main picture, let's say. So starting from the top, like I said, we are driven by the use cases. We have three main use cases, so the smart home, the industrial IoT, and the automotive. And like I said, we have the open call to actually even extend and broaden this range to other applications out there that are interested. And then we go one level lower and we have the middleware, so the tool chain that will allow us to convert all these nice applications and map them to the different hardware that we are supporting. So we have an optimizer for the models and to develop and to map them to the hardware. And then we have two tools. One of them is to emulate hardware before development, and the other one is for benchmarking, helping us in the benchmarking. Then we go one level deeper, and we have the accelerators. And in there we have a bunch of off-the-shelf accelerators that we tested. We have development in FPGA dedicated accelerators with different mindsets for each of them, and I will go a little bit over that later on. And where do you put all these accelerators? In some neat boxes that Kevin is actually going to show us later on. And we have boxes for all sizes, so from the small to the big. And that just depends on the placement that we are putting these boxes and these devices. So our goal is to cover the compute continuum from the far edge up to the cloud. And that's why we have all this complete solution to offer. So starting from the cool use cases. So the first one is automotive, and well, personally, Chalmers, another of the partners, we are coming from Göteborg, many of us, and you know, the hometown of Volvo. You have to have a Volvo there, you see, but Volvo is not part of our project, by the way. This is a Veoneer picture. It's one of our partners. And what we are trying to do is obviously try to attack this immense problem of autonomous driving, right? And in this case, the really challenging thing here is how can we distribute efficiently the problem across the different layers of the hardware that I have just shown you. So when we have a complex problem to solve, what should be solved at the far edge, close to the sensor inside the car? What can we solve on the base station? And if you heard in the morning now, we have millions of base stations going around, so that's really nice. So because while you are driving, you can offload things around. And then if it doesn't fit, then we will offload it to bigger and bigger systems, depending on different factors. And we also cover this, and I'll show you a slide later on. So in here, really the important thing is how do we manage all this complexity and distribute it over all the little devices that we have on the compute continuum. Then we move to the industrial smart industrial IoT use case, and we have two sub use cases there. They all come from the same partner, Siemens. So in this case, you actually also saw, if you were here at the keynote, you also saw this similar picture of a motor. What is the big problem there is when is this motor gonna fail? And if we know ahead of time, we can prevent huge amount of expenses in having the, for example, production line down, right? So what we want is to put a really tiny device close to this motor that can predict, given the measurements that are being done while the motor is functioning, when this failure point is going to happen and proactively act on that. So here, actually, the challenges are that we want a device that is very low power and super efficient. And this was, I can share with you, very strange to me when I saw it for the first time, because I was saying, this is a high power motor. Why do I need efficiency? Well, simple thing. This is AC and our devices are working in DC, right? And you really don't want to have a lot of these things. So you want a little device that you just couple there, is listening to the motor. Whenever it hears something strange, well, let's predict that we need time to switch it off and shift it to a new one. So that's cool. Then we have another one coming from the same partner, and this is also a really nice example for the industry. And here we are talking about cabinets where there is a lot of switching in electricity again, and it's the problem of having arcs, electrical arcs. Electrical arcs can cause fires, and therefore you can understand destruction. Nothing that we want to have. And here the challenges are quite tough because what we want is very high accuracy. We don't want false positives or negatives. Both of them are bad. I don't want to predict something that is not going to happen, shut it down, and then lose my production. I don't want to not predict the arc, because then I'll have the fire and the destruction, so I really need accuracy here. And on top of that, I need it really, really fast, because an arc doesn't give us a notice of half an hour, right? I'm gonna give an arc in half an hour, okay? So come, finish your coffee. No, it's not gonna be like that. So, challenging. The other use case we have is in the smart home, and this is the smart mirror that you can see over here. So let me use the pointer. There. So we have the smart mirror over there. And in this case, obviously what we want to do is provide a system that can help with improving the quality of life for people that need some sort of assistance. And we have this use case that you can identify, take control of several things inside the home. And the challenges here are, if you are at home, and you know this from probably the scandals of Amazon or Google devices that are actually snooping on what we are doing, we want to avoid that. So we want privacy. What is the solution for privacy? Do it on the spot. Don't share the information. So in this case, we are putting the emphasis on the far edge that need to solve the problem. And as complexity becomes higher, then we need to have systems that can attack these issues. This also is a quite complex application because it has different types of demands in terms of what the AI is performing. So it's recognizing the face to know who it is, it's recognizing objects, gestures, and speech. And you need to combine all that in the small device. So how do we combine the multiple models and be efficient? And that's what we need to answer in this use case. So this is the support that and the challenges that we were faced to that then drive us to develop hardware to do all this job efficiently. So starting with the tool chain, if you remember that image that I showed you on the bottom of the use cases comes the tool chain part. This is an overview of our tool chain. We have our own model zoo, so with some models that we consider are relevant for our use cases. We had this discussion with the use case leaders and gathered all these models. Then we have development of an optimization engine for these machine learning models and mapping tools to the hardware, which will then run on, again, like I said before, the cool boxes that we'll see on the next presentation. Okay. And inside the cool boxes that you'll see in the next presentation are the even cooler accelerators. So those we have summarized that we are trying to target 4 different types of accelerators, we could say so. So the first one is off-the-shelf accelerators, where we took a peek and a snapshot of what type of accelerators are there in the market right now and did a very in-depth evaluation so that we could understand what the use cases could use them for. And we will have more of this again in the upcoming presentation. Then we have a middle category over there. Let's see if it works a bit better from here. So then we have this middle category here where we have reconfigurable deep learning accelerators. These are FPGA-based accelerators where we have addressed static reconfiguration or dynamic reconfiguration. And this, you will see much more of it on the last talk that we will have today here in the session. And last but not least, we have the Co-Design Accelerator, which is that one that will work together hand in hand with the deep learning models. And that's the one that actually Chalmers is developing and responsible. So we all know that Moore's law is running out of steam. And this was an interesting discussion we had last night, that we can rename the nanometer technology points, but we cannot avoid physics. So that's it. And it is well known now that we need to move on to domain-specific architectures. So this is our motivation to go into this direction. We need some flexibility and efficient accelerators to address all the issues that I showed you on the different use cases. And this is a term that I've seen mentioned in some places called algotecture. So it's the merge of algorithms and architecture. So this is the co-design part that we want actually to investigate in this project. So like I said, this is going to be covered on the next presentation and the middle part on the last presentation. But right now, I can give you more insights of the co-design one. So first of all, what is co-design? And we all know the word co-design, but it's good to have some definitions explained here because sometimes we understand it in different ways. So co-design is designing together the software and the hardware. And that's what we want to do. But there are people that also call co-design just by doing the one-way thing. So for example, design the software for the hardware. So software or hardware-aware software optimizations. So these are things that we are doing currently, right? And if you are into the machine learning world, you have learned all these words that are here, these keywords that are here. So we have models that people train them, they are huge, and then we say they need to run on very small devices, so let's compress them. And what we usually do for compression is do some sort of quantization where we pick up the data formats and we shrink them to smaller data formats, or we just say these arcs are not really important, so we just throw them away and we do pruning. So we have more compact models. These quantizations will be aware of the hardware that is supporting. So if I have 8-bit functional units, 4-bit functional units, then I will be able to do quantizations for these bits. What I cannot do is 3-bit quantization if I don't have 3-bit support. And in there, the reconfigurable part will kick in. So this is also a link for if I have off the shelf or if I don't. And we are trying to look for all these things inside the project. Neural architecture search is actually an interesting thing, is using machine learning to build machine learning. So how you can have a machine learning train and come up with a better model. If we put the characteristics of the hardware, then this is what we would be doing in the co-design part. The other way of the co-design is to say, let's do hardware to map the software, right? And if we're just doing on this single direction, what we will probably think about is how to map into, for example, reconfigurable hardware, some sort of software that we have. And again, so data flow designs and so on, they have been explored. But really the interesting thing is how we can do the handshake between the two. So how can we pick up a model, try to optimize for certain hardware characteristics, try to put it in hardware, and then realize this is not really working the way that we thought, or giving hints to the software by saying, if actually you did this optimization, it would be really much better in terms of the efficiency on the hardware side. So we could say, I'm trying to map this machine learning into an FPGA, but by the way, the quantization you used, it doesn't fit the FPGA. So let's give a hint to the software and say, use another quantization to reduce even more so that we can shrink it and work it there. This or other things. There are things that are dependent on the hardware, but there are things that are dependent on the application too. So what if the conditions change? And for example, just to give you a quick example, in the automotive, driving at daytime in the city is probably much different than driving at night on the highway. So maybe the model will change for that. Maybe the hardware can change for that too. And this is where we will have this co-design and reconfiguration even at runtime. How can we achieve this in an efficient way? So things we are looking for the co-design part are, we split it into two categories. One that is oblivious to the model, so it doesn't care about the models, and then the other one is specific to the model. And obviously you have this hint that, okay, if I'm specific to the model, I'm doing very tailored software, hardware for this. That is in a way true. If I'm more oblivious, then I'm doing more generic, I can fit more things in. And we are looking into these two categories. So in terms of oblivious, there are some cores that you can configure, some IP cores for accelerators. This is just an example. It's the TVM Vita that is available online. So we are testing this, how we can use it on the FPGA. And then we have another approach, which is using a tool from Xilinx called FIN. And this is to map the data flow of the whole model inside the FPGA. So all the layers are running at the same time. And this is just an overview of the project, so I'm not going into details, but if you have any questions about this, we will be happy to take them later on and go more into details on these things. So, like I said before, one of the key things that we want to find here is, yeah, we can use all these tools from out of the box, but then having the co-design and having the people that are developing the software tools that are doing the mapping together in the project will give us the advantage of giving this feedback directly to those people, getting the optimizations done to the hardware, and do the cycle in an iterative way until we get the best design. So mixed precision, maybe not all layers will be quantized to the same thing, or sparsity aware into different layers so that we can actually do more hardware optimization. So all these are things that we want to play in the project. In addition to this, I did just computation, but there is obviously the memory side. So we also have some focus in Chalmers on how to better design memory hierarchy and different memory buffers and structures to support these accelerators that have different needs at different times. And then, like I said before, we want to put all these super cool accelerators inside the boxes, and I'll not go over this anymore because you'll get the details in a few minutes. But just have in mind that we have different boxes for different needs, and they will be hosting different accelerators too. If you remember the big picture at the beginning, that we had two vertical bars that affect all the work that is being done in the project. One of them is the requirements. So working very closely to the use cases, we were able to identify the requirements of the use cases and try to bring them down through all the development process. And in this sense, what we did was we gathered different criteria that the use cases were expecting from the execution into different categories that you can obviously see here. But I would like to highlight is that the end goal of this is to be able to deliver systems that are offering safety by design, ethical by design, security by design, performance by design, and so on. So we put quality of service into different types of categories like ethics, security, safety, and privacy, and then we map these to the hardware development to satisfy these requirements for the use cases. And we have developed a complete framework within the project. The other bar on the other side was about security, privacy, and trust. And I told you already that there is obviously interest in touching these areas. And you probably are aware of the trusted execution environments that are offered in the standard processors, like the SGX for the Intel or the Trust Zone for the ARM. Within the context of this project, we also were working, we have a special group of the project partner working on extensions of these and something called WebAssembly. And we are going, if I'm not wrong, we are going to extend this to the RISC-V support so that we can put in integrated with the rest of the project. And also within this category, there is robustness, trying to satisfy robustness concepts. And in this case, what I would like to highlight is, so when we talk about automotive use cases, it's not really something like we have, like my laptop right now, just the battery died and that's okay. But if we are driving a car and we are actually reading the newspaper because the car said it's okay to read the newspaper or watch the YouTube while it's driving, and then suddenly something fails, we need to take care of that, right? So this is what this is there for. It's actually monitoring what is happening and trying to take actions to avoid bad things from happening. And that's what we are working also to try to satisfy and attach this in the project. In terms of tools, more of these tools in the tool chain, I would like to highlight two important tools that we have within our project. One is Renode. This is offered by Antmicro, and this is an open source for the development of basically is how we can easily develop RISC-V based coprocessors, for example. And we will be also using this tool for our internal use. And then we have Kenning, which is a tool that is focusing on performance analysis. And in here, we can add different models, different hardware pieces, and get statistics of what is happening in terms of performance and different metrics, which is quite a useful tool for analyzing all these things that we have in the project. Like we have many different models, many different pieces of hardware. So just to summarize, and I think right on time, to keep you in mind of the goals of this project. So VEDLIoT is here to develop a platform from the top to the bottom. So in terms of hardware that is scalable, heterogeneous, distributed, being able to cover all the points in the compute continuum with focus on dedicated accelerators to solve the real problems that we have for the use cases, but also be flexible enough for tomorrow's use cases. And we are happy to have this open call so that we can actually test our technology with different use cases, and use cases come and test with our technology. So again, it's a type of a co-design. And the use cases we are currently focused is industrial IoT, automotive, and smart home. And with this, I think I would like to pass on to the next presentation. But before that, if you have any question before we go on,